Alrighty, now some more specific types of probability. And today in this lesson, we're going to talk about mutually exclusive events versus independent events. Now, something is mutually exclusive if the two events cannot occur at the same time. So looking at this diagram here, it looks very similar to our Venn diagrams or our two-way tables, but notice that there is no intersection between A and B. They cannot occur at the same time, meaning if there's no intersection, the value of their intersection is 0. And our general addition rule becomes the following. P, A, or B is just the probability of A plus the probability of B. Now, keep in mind, this is very similar to complementary events where they also can occur because either A occurs or A does not occur. But note the key difference here is that in mutually exclusive events, they just cannot occur at the same time. Whereas with complementary events, the sum of the two events must add up to 1. Here, this could be 0.3 and this could be 0.6. And we'd be okay. But with complementary events, they have to sum to 1. So now let's look at the other side of the coin here, independent events, where the outcome of event A does not influence the outcome of event B. Thus, the probability of A and B, well, if A happens this percentage of the time that B happens, we would just take the product here. The and means to multiply. Now, think about it this way, is that let's assume the probability of landing on a heads when you flip a coin is 50%. So if I do that 2 times, it's 50% times 50%. The fact that I should get 2 heads in a row should be about 25%. Or other independent events could be like, I'm right-handed and you could be right-handed and another viewer could be right-handed and 117 other people could be right-handed, but that 118th person could be left-handed, and that's okay because our hand dominance is independent of one another. So mutually exclusive cannot occur at the same time. Independent means that whatever happens to A does not influence what happens to B. Now, there are some special rules here. And let's look at the following. On the AP exam, you have to be able to show any one of these 3. Now, this is the more commonly shown one these days, is the probability of A given B equals the probability of A. This just says that regardless if B happens, since it has no influence, the probability of A is the same whether or not B occurs. And on the converse of that, the same logic applies to B given A. If A and B are independent, then the probability of B does not change given that event A has occurred. And that just brings us to this right here. You're probably wondering, well, A and B, why does that equal A times B? Well, thinking back to when we use probability tree diagrams, and don't write this in, just showing you a proof here, is that we've said that P of A given B was A and B over B. So we see the intersection, and I'm doing some sloppy notation, sorry. This is what we got for our notation. But here, if the events are independent, then A given B just becomes A. So A and B is A times B. You don't need to memorize that. You don't need to be able to prove it. It's just where this multiplication rule of independence comes from. Now, none of these formulas are on the AP exam, so you do need to memorize these, but pretty similar. This and just means multiply both. And this one, if they do not influence one another, then regardless if B happens, A should be the same. And regardless if A happens, B should be the same. So let's take a look at an example here of what an AP question might look like. Now, it could give you a written description, but most times it's going to give you these 1, 2, 3 statements, and it's going to give you some probabilities, and you are going to need to distinguish what is going on with those probabilities. So let's take a look here. We have P of A, P of B, and P of C, and it says these are 3 mutually exclusive events. So A and C, if it's an intersection, well, it's mutually exclusive. They cannot occur at the same time. So off the bat, I already see that this is an area of concern. That one's going to be false. Here, they're mutually exclusive, so the probability of A and B should be 0. That's going to be true. And I don't think I talked about this, my bad. Here, since the intersection is 0, the general addition rule, which is A plus B minus A and B, well, A and B is 0. So the general addition rule is just adding the 2 probabilities together. So the probability of B or C, given that they're mutually exclusive, is just going to be P of B plus P of C. And that's just because even if I were to subtract out this area, well, this equals 0. So subtracting 0 isn't going to change anything. So this is true and this is true. This is false. So we get that statements 2 and 3 are correct for us. So that's an example of something you might see on the AP exam. They'll give you some different probabilities and they'll ask, are they mutually exclusive or are they independent? And now one important thing to note is that they can never be both at the same time. They are either mutually exclusive or they're independent or they're dependent, but they have to be some type of these probabilities. So if they cannot occur at the same time, those are mutually exclusive. If the influence of one does not influence the other, then they're independent events. But you would just have to check these properties here to categorize the type of probability that it is. So here's a two-way question. Let me give you a few moments with this one. So go ahead and pause the video, try it out for yourself, look over the last example, and we'll come back together and work this out. Alrighty, so hopefully not too challenging, and hopefully you're remembering your rules from the last few lessons about probability. So let's check here. You should have gotten statements 2 and 3. We'll actually go over this in class, but you can see here that here's the work for you. I trust that you can read some mathematical symbols, but you should have gotten statements 2 and 3 were correct. We'll go over this in class, so no worries. Now, let's take a look here at something that's a little less common on the AP exam, but still good to know for your general probability knowledge. So suppose we have PA and P of B. Now, if we want PA and B, because they are mutually exclusive, this means A and B equals 0. So PA or B just equals the sum of these two values. And sorry, I do not know why my handwriting is so sloppy, but here we go. We get 0.57, and I skipped a step with my work here. My bad. But I know you all will definitely do your full steps. Now, if A and B are independent, then that changes things. Then that means that A and B is equal to their product. So here, the probability of A or B is going to still be the general addition rule. However, for the intersection probability, instead of writing PA and B, I know that's going to be P of A times P of B. So when I get this result here, well, I already know that P of A plus P of B is 0.57, and then I need to subtract out the 0.3 and the 0.27. So that's going to give me that if these two events are independent, then PA or B is going to equal about 0.489. So these are just very mathy probability skills that you might see when you take a probability or stats class in your undergrad career. And now lastly, here we've got this situation. Let's find P of B complement, assuming that A or B is 0.64 and A is 0.37, and I know A and B are independent. So let's write out what we know. I know that A or B, and I'm going to switch to some logic here, equals PA plus PB minus PA and B. However, they are independent, meaning that here the intersection will be their product. Now, I'm just going to sub in what I know. Here's 0.64, probability of A is 0.37. I do not know the probability of B, but I do know probability of A. So here we're going to just combine some like terms going on, so that will give me about 0.27 here. And then you must be asking yourself, okay, well, what about this section? Because I have 1 PB minus 0.37 PB. How could I get those together? Well, treat it like a variable. They both have P of B, so 1 minus 0.37 is just going to be 0.63 PB. And then from there, we'll do a little inverse operations to gather the result that P of B is going to be about 0.4286. So the probability of the complement will just be 1 minus the probability. So 1 minus 0.4286 will give me B's complement, which will be roughly about 0.5714. So sorry to get all lecturely on you there, but those are just some more ways you could see probability show up on the AP exam or probability show up in general. So I have a few word problems here for you. I'm dealing with mutually exclusive events. There is a particular template that we will use when asked if events are independent, but can't show you everything on YouTube, so I will definitely give you the interpretation in class. So what I need you to do now is go ahead and pause the video and try out the next page of examples, and then again, we'll come back and review it together. So go ahead and try now. Alrighty, so hopefully not too challenging. Explain why the events are mutually exclusive. You should definitely mention something about the two events not being able to occur at the same time. So here, either a person can have a cholesterol level of 240 and greater, or between 220 and 239, but they cannot have two cholesterol levels at the same time. Thus, since the events cannot occur at the same time, they are mutually exclusive events, meaning that their intersection is 0 because they're mutually exclusive. And the general addition rule applies here, so that the probability of A or B is just the sum of the probabilities here, which is 0.45. And lastly, again, this idea of like a broken noodle. I have this noodle that has 3 sections. I already know A and B. So to find the probability of C, I would use the complement rule based on the probabilities that I already know of. And here, that probability would be 0.55. And then lastly here, this example, I accidentally copied twice, once in 4.1 and then once here. So hopefully you still remember how to do this. But you can see here that now we used to treat this as a probability model, but now we see that these events are actually mutually exclusive because either a mother has 1, 2, 3, or 4 or more kids, but she cannot have some weird variation where she has 2 and 4 because that would be 6 and that would fall under this 4 or more. So again, just being able to look at either a two-way table or a probability model and determine what the events are, either by logic, some geometric rationale, or even formulas. And lastly, I did not mean to rob you all, but here are some sentence stems that you will need for this unit. I did not provide a space for you to write it, so you're just gonna have to freehand this one. But events A and B are independent since P of A equals P of A given B equals this value. So you have to include whether they are or are not, what your justification is, meaning is it the multiplication rule, is it P of A given B, is it P of B given A, and then you have to provide some numeric justification. So these are the two sentences that you'll see on the FRQs when they ask you, are the events blank and blank independent of one another? Yes, they are because this. No, they are not because this, etc. So just to put a nice little bow on it, mutually exclusive cannot occur at the same time. Independent events have no influence on one another. These formulas are not on your AP Stats formula sheet, so you do need to start memorizing these, writing them down, put them on your yellow sheets. But alas, that is going to conclude our lesson here on mutually exclusive and independent events. In our last lesson for the first half of Unit 4, we're going to talk about successive events. So stay tuned as we wrap up our study on probability.